So we're back with Chapter 5. We're going to continue our discussion of the control volume approach, and this time we're going to apply the Reynolds transport theorem, which comes from the control volume approach, to the continuity equation. The continuity equation is used basically for mass. So here we are with our learning objectives. We're going to be doing both sections 5.3 and 5.4 together because they're both quite short. Describe and apply the continuity equation, and we're going to describe how the equation is derived, just briefly. And so let's skip ahead now to, let's start just at the end of the Reynolds transport theorem section, slide 36 here, where we wrote the equation, basically the theorem here in words, where we have the rate of change of the property we're interested in a closed system. That's going to equal the rate of change of that property within the control volume plus the net outflow of the property through a control surface. And so we're going to be starting to apply this equation to mass and to solve problems that require our understanding of flow through control volumes and control surfaces. So we remember that this equation can be written in different forms, and in particular this form is going to be important here, where we have the change, the local change, the Lagrangian change in time, versus what's accumulating in the control volume, plus the outflow minus the inflow. So this form of the equation is going to be important here when we talk about mass. So section 5.3, the continuity equation is a law of conservation of mass applied to a control volume. That's what it is. So to begin, let's ask ourselves, what is the rate of change of mass in a closed system in the Lagrangian local reference frame? So what is dm dt in a local reference frame? This is an interesting question because we know that mass cannot be created nor destroyed. So this actually, in a Lagrangian sense, actually equals zero. So the left-hand side of our equation is going to cancel right now. It's going to go to zero. The second question, okay, so we've answered that question. The second question is, if B for a closed system is M, if we're interested in the extensive property B here, this is our extensive property, what is little b, the intensive property? Do you remember what little b was equal to? Little b was defined to be equal to big B over M, the per mass, the quantity we're interested in per mass. But of course, we're interested in mass. So this is just mass over mass. So in our case, little b, in the case of the continuity equation, applying the Reynolds transport theorem to continuity, little b, our intensive, this is our intensive parameter. Our intensive parameter is equal to 1. So that's going to simplify our equation even more. So when we have this, we note that the left-hand side here, dm of a closed system, dt, is going to be equal to 0. So this thing is going to be equal to 0. That follows down to this equation here. And that's the general form of the continuity equation. However, if we've seen that if we have a number of inlets and outlets through a control surface, as I mentioned in the last lecture, and as I drew your attention to at the beginning of this lecture, that this is the form of the equation that's going to be most useful to us, where we look at the rate of change of the mass within a control volume to the outflows and inflows. Now, let me just draw you a quick picture here. A good example of this might be some sort of sink or tub where we have some water flowing into the top of it, maybe through some nozzle here, and we have an outflow coming out. Now, if we draw our control volume to be, let me draw another, grab another color here. If we choose our control volume to be something like this, then we could see how the fluid, if the inflow is greater than the outflow in this case, we can see how the fluid might rise and start to accumulate within our control volume. So that's where this term comes in. If basically in this equation, if the inflows are greater than the outflows, this is going to be positive. Note that if we move these two things, which we'll do in a minute, if we move these two things to the other side, dm for the control volume dt actually equals the sum of the inflows minus the sum of the outflows. So physically this makes sense that if in fact the water in the sink here goes up, the inflow is greater than the outflow out the bottom here, then the water will go up in the sink, and this will be a positive dm dt. So the physical interpretation of the continuity equation is this. The first term over on the left side now is the rate of accumulation of mass. This is just accumulation of mass inside the control volume. We've moved these two things over to the other side. This equals minus the integral of rho v dA dot dA, and in the general form, in the kind of the simplified inlet-outlet form, we have that equaling the sum of the inputs minus the sum of the outputs through the control surface now. So this is the rate at which mass enters the control volume, and this is the rate at which mass leaves the control volume. So the continuity equation gives us what we expect out of the physics, that if the inflow is greater than the outflow, we're going to accumulate mass within our control volume. So we have these working equations. We just talked about this equation, and we talked about this equation. These are in their the general form and the simplified form. We also know that for pipe flow, this can be reduced even further to just rho 2a2 times v2, the velocity, times rho 1a1 times v1. Now, for density, for gases, the density can vary, so we need to keep rho 2 and rho 1 in here because depending on what's going on inside a pipe, say, with gas in it, the density might be changing. But for liquids, we can usually, as we've stated before in Chapter 2, we can usually impose the constant density assumption, and we can cancel these two densities. And then we have our familiar equation that A2 V2 equals A1 V1, which we've been talking about in terms of volume flow rate. And that's really it for section 5.3. Obviously, we need to learn how to apply this to real-world situations, which we'll do. And we'll just take a quick look at these steps for applying the continuity equation. So step 1 is selection. We want to select the continuity equation whenever we see a problem that deals with flow rates, velocity, or mass accumulation. When these are involved in the problem, we want to turn to the continuity equation and apply it. It's important to be able to sketch a proper control volume by locating control surfaces. This is actually important. Let me choose a red pen here. By choosing control surfaces that cut through where A, you know information, and B, where you want to know information. So we want our inlets and outlets. We want to know some of the inlets and outlets, and where we want to know, we want to identify where we know the information at some of the inlets and outlets, and then we want to also have the control surface cross over where we don't know the information. So sketch it, label it appropriately, and note that it is common to label the inlet port as section 1 and the outlet port as section 2. This is just customary. Then in analysis, write down the continuity equation, perform a term-by-term analysis to simplify the equation, to simplify it, and to check your units. Check the physics and make sure that inflow minus outflow equals accumulation at the end of the problem. So that's it. There's a whole series of examples, but we'll either do these in class or we will I will put together a lecture with some of these examples as well. So thank you very much.